Hey, what's going on guys? Tanmay here for Simple Snippets, and let's continue with our AVL tree topic. And in this video, as the title of the video suggests, we are gonna solve two numericals based on insertion in AVL tree and rebalancing of an unbalanced binary search tree. Now as you can see on the screen, these are the four different basic rotation cases based upon the different orientations of imbalanced binary search tree. This is something that we saw in the previous tutorial. Along with that, this next image is again the same four cases, however this time it is with more than 3 nodes. So this is something that we've seen in the previous two tutorials, and I'm guessing you guys already know that. Along with that, I am assuming you guys already know what is AVL tree, what is binary search tree and whatnot. If you have any queries, just check out this entire playlist, this DSA course, and all your doubts will be cleared. Coming back to today's topic, we are going to solve two numericals. The first one is going to be balancing a unbalanced binary search tree or imbalanced binary search tree and converting it to AVL tree. And the second numerical is where we are going to get a insertion sequence where we will be getting a number of nodes to be inserted. And as we start inserting them, at some point the binary search tree, which is balanced, that is it is a AVL tree, will become unbalanced or imbalanced, and then we will do the rotations. Okay. So for all this, as I mentioned, the concept of rotations needs to be very clear. The concept of AVL tree should be clear. Now with that introduction, let's start off with first numerical. Okay, so the first question is convert the following imbalanced binary search tree to AVL tree using rotations. So currently we've been given a binary search tree which is imbalanced, and we have to perform some rotations on this and make it AVL tree. Now how do you find out whether it is imbalanced or not? In case if this imbalance keyword was not given in the question, you simply have to calculate the balance factor, which is given by left subtree minus right subtree for every node, and this balance factor has to be in the range of -1, 0 and 1, and only then you can say that the binary search tree is balanced, which means that it is a AVL tree. Now in case if the balance factor goes below -1, that is -2, -3, or it goes above 1, which is 2, 3 or whatever be the number, then you can say that the binary search tree is imbalanced and it is not a AVL tree. Okay, and then it will need rotations. So let's calculate the balance factor. So this is for every node. So let's start off with calculating the balance factor for n1, which is the root node over here. Okay, so LST, what do I mean by LST? It means the height of LST, okay, and not just LST. Okay, keep that in mind. So the height of left subtree for n1 is going to be height of this entire part, correct? And the height of right subtree is going to be this, which is nothing but a blank side. So just by observing this, the height of this tree is going to be the distance between the root node for this left subtree and a leaf node, which is one edge. So it's going to be 1 and minus, because we have to do a subtraction. What is there to the left subtree? We have nothing. When we have no nodes in a tree, the height is usually considered as -1. So you have to do 1 minus -1, which will give nothing but 2. Correct? So calculating the balance factor for the first root node, we are getting 2, which itself says that it is imbalanced because it is not falling in this -1, 0 and 1 set. Correct? Similarly, when you calculate the balance factor for n2, it is going to be 0, for n3 it is going to be 0, for n4 it is going to be 0. I'm not showing the balance factor calculation for every node because if you've seen the previous tutorials by now, you should be able to calculate it very easily. So now we've detected that the problem is in this node, that is the imbalance is happening at this node. So you can consider this as the critical node or imbalance node. And the next thing is that the imbalance is happening towards the left, right? So you go from n1 to n2, one left, and you go from n2 to n3 as the second left, correct? So you can see this is a left-left imbalance. You can also say that this is left-right imbalance, but since the left-left imbalance is pretty straightforward, and in that we just do a right rotation, correct? So we are going to consider n1, n2 and n3 as the 3 nodes which are going to do the rotation. So whenever you do rotation, remember you are going to take 3 nodes into consideration, and remaining all the rest of the nodes are considered as extra nodes which will be later on added after the rotation. So this is something that we saw in the previous tutorial where we were doing the rotations with more than 3 nodes. So clearly you can see that this is a left imbalance, which means that you have to do a plain right rotation. So when you do right rotation, what happens? you can see over here, this is a left-left imbalance or left-left case. We have to do a right rotation. So in right rotation, if you observe, this N2, that is the center node, becomes the parent node. So N2 is shifted left and N1 is taken down, correct? So over here also we have N1, N2 and N3 as the three nodes. The center node is N2, correct? So when we do a right rotation, what will happen is this N2 will go to the top. The value inside N2 is 45, right? Let me write 45. So when N2 is taken to the top, N1 goes below. So let's write N1. And this N3 becomes the left child. You can see over here, N2 goes to the top, left child is N3 and right child is N1. So over here also N3 will become the right child. So let's write N3 as the right child. What are the values of N3? N3 is 3 and N1 is 87. And if you observe, these are also following the rule of binary search tree. So what is the principle of binary search tree? For every particular node, the right child should be having a larger value and the left child should be having a smaller value. So that rule is also maintained over here. So now we've done a basic right rotation, but you can see we still have one more node N4. So where does this go? Now in the original tree, N4 was towards the right of N2. So after the rotation also, N4 needs to be towards the right of N2. And of course, since N4 is greater, that is 77 is greater than 45, it is but obvious that it will be towards the right of N2. So that hierarchy or that relation has to be maintained over here also. So we will go to the right of N2, but now N1 has come to the right of N2. So you cannot have N4 over here. So now we have to compare N4 and N1, and you can see 77, which is the value of N4, is smaller than N1. So of course it has to go to the left of N1, correct? So N4 will come over here as the left of N1, and in the original tree also, which was imbalanced, if you observe N4 is towards the left of N1 only, because to reach to N4 from N1 we will have to go to the left. So even that hierarchy is maintained. But now if you observe, this tree has become balanced. Just by a single right rotation we have balanced this tree, and if you calculate the balance factor is going to be -1 for N2, for N3 it is going to be 0, for N1 it is going to be 1, and for N4 it is going to be 0. You can quickly calculate it, but all these values from -1 to 0 to 1 are in our acceptable range. So now we can say that this is a balanced binary search tree, which means that this is a proper AVL tree. Okay. So this is how you convert an imbalanced binary search tree to a AVL tree using rotation. And this was a fairly easy scenario. So this is one type of problem where you will already be given a imbalanced binary search tree and you have to convert it to AVL tree. Okay. We'll do more examples on this type, but now let's see the second type where you have to create a AVL tree using an insert sequence. Okay. So here's a question where you have to create an AVL tree using the insert sequence as follows. So you've been given 55, 66, 77, 15, 11, 33, 22, 35, 25, 44, 88, 99. So you have to create a AVL tree. Now we all know that AVL tree is nothing but a balanced binary search tree. So the insertion of AVL tree is also going to be same, just that after you insert a new node, at every step you will have to check the balance factor to check whether that tree is becoming imbalanced or not. And in case if it becomes imbalanced, then you have to do the rotations. Alright, fair enough. So let's start with the insertion. The first node is 55. I'll write 55 over here. Let's name it N1. Or you know what, we don't even have to name it N1, N2 and N3 to add a little bit more complication to that, because these numbers are all unique numbers. We are not repeating any numbers, right? So let's write 55 as it is. Okay, so this is our root node, and as I mentioned, as soon as you insert a new node, what you have to do, you have to calculate balance factor. Of course, since there is only one node in the AVL tree, the balance factor is gonna be 0 only. So this is a proper AVL tree, correct? This is still a AVL tree. Let's move forward. We've done 55. Let's insert 66. So 66, when you insert 66, 66 is greater than 55. So where should 66 come? 66 should come to the right of 55. So I'm going to write 66 over here, right? Okay. Now again you'll have to calculate the balance factor. Now this time the balance factor for this node 55 is gonna be left subtree, which is nothing, minus right subtree, which is only one node. So minus 1, because there is nothing to the left subtree, minus what is there to the right subtree, we have one node. So when you have one node in a tree, the height is considered as 0. So minus 1 minus 0 is going to give you minus 1. So let's write minus over here. What is the balance factor for this node 66? It's going to be left subtree minus right subtree. Since we have nothing towards both the children, it is going to be 0 only. So the balance factor for this node 66 is 0. And since the balance factor, which is given by height of LST minus height of RST, which has to be in the range of minus 1, 0 and 1, is satisfied, you can say that this is still balanced and this is still a AVL tree, correct? Alright, let's move forward. Let's now insert 77. So 77 is again greater than 66 and it is greater than 55, so you'll have to come to the right and then come to the right. So you'll insert 77 over here, correct? Once you do that, now you can see we are getting an imbalance over here. So when you calculate balance factor now, for this 55, you have nothing towards the left of 55, which means that the height of the left subtree is minus 1, minus the height of right subtree now has become 1. So there is one edge between the two nodes, so that's why it is 1. Now minus 1 is now going to be 2. That is minus 2. Okay. Height of this 66 is going to be minus 1. Height of 77 is going to be 0. So we have detected an imbalance at this node 55. So consider this as the critical node. Where exactly did the new insertion happen? 77 was the new insertion that happened towards the right. So the imbalance is clearly towards the right. You can see we have to go right and then right. So this is a right-right imbalance. Just by looking at the structure also we can see that this is a right-right imbalance. So what happens in a right-right imbalance? This is what happens in a right-right imbalance. You do a left rotation, and when you do a left rotation, the center value N2 you can see becomes the new parent. N1, that is the top value, becomes the child over here, and N3 remains the right child of N2. So if you apply this same logic over here, what will happen? The center value is 66. So 66 will go on top, 55 will come down, and then we have a new structure, correct? So let's do that. So I'll take 55 down over here, and then you get this kind of structure which is balanced. You can clearly see. So this is what left rotation would look like, correct? Alright. So now we've got a new root which is 66. Let's proceed further and insert more values. Now we have to insert 15. 15 is smaller than 66. 15 is smaller than 55. So 15 will come over here. Now you have to again calculate the balance factor because a new insertion has happened. So balance factor, if you calculate, the left subtree is these two nodes, which means the height is 1, minus the right subtree for 66 is this one single node, which means the height is 0. So the balance factor is going to be 0. Balance factor for 55 is going to be 1 because the left subtree has only one node. So that would be 0 minus, and the right subtree has nothing. So you have to do minus 1. So 0 minus minus 1 will become 1 because minus minus will cancel out, basic mathematics. So height is going to be 1. For this node the height is going to be 0 because there is no children. For this node also the height is going to be 0 because there is no children. So all these numbers are well in our accepted range. Let me just write it over here again. The range has to be minus 1, 0 and 1. So hence it is still a AVL tree. So we don't need any rotations. Let's proceed further. Alright, let's insert 11. 11 is smaller than 66, you go to the left. 11 is smaller than 55, you go to the left. 11 is also smaller than 15, so you still go to the left of 15 and add the new node over here. As soon as you add this new node, you can see clearly there is an imbalance now. So again you'll have to calculate the balance factors first. So let's do that. So calculating the balance factor for node 66. So left subtree is this node which has 3 nodes. So height is 2. So we have 2 minus, what is right subtree? We have only one node. So height is 0. So 2 minus 0 is equal to 2. So immediately we've got one imbalance. Let's calculate the balance factor for other nodes also. So this node the balance factor is 0. For this leaf node the balance factor is 0. For this node 15 the left subtree is 0 minus the right subtree is minus 1 for 15. So minus 1 is gonna be 1. So this is 1. For this node that is 55 the left subtree is these two nodes, correct? So the height is 1. So 1 minus, what is the right subtree for 55? We have nothing to the right of 55. So it would mean minus 1, right? So 1 minus minus 1 will again give you 2, correct? So you can see now there are two nodes which are imbalanced. So we have to pick the one which is at the lower level and start balancing that. So when you balance this node, sometimes or most of the times what happens is the upper node also gets balanced first. So where did the imbalance happen? It happened towards the left because the insertion was towards the left. Starting from this node, if you go to the top, one node up, is there imbalance over here? No. You go one node up, is there imbalance over here? Yes, because this is 2 and 2 is not in our acceptable range of balance factors. So you can see this is a left-left imbalance because if you again traverse back to the new insertion, we have one left and we have one more left. So again this is a left-left case which is depicted over here. So in this scenario what do? We do a right rotation, and this time the nodes that we are going to consider for right rotation are 55, 15 and 11. These are the three nodes that we are going to apply the right rotation first. Now when we apply the right rotation, you can clearly see the center node N2 becomes the parent node. So in this case the center node is 15. So firstly just write the upper nodes as it is. They are not going to change. So let's do a right rotation. Okay. So just keep this structure in mind. The center node becomes the new root node and N1, that is the top node, comes as the right child of N2. Okay. So keep this in mind. So when you apply right rotation, first let's keep the root node 66 as it is, 77 also as it is. These guys are not changing their positions, right? Now let's apply the right rotation on these three nodes. The center node, as I mentioned, becomes the new root node. So 15 will be taken to the top. So we have to write 15 over here. 55, which is the top node, was taken to the bottom. So we'll write 55 over here. And 11 will be the left child as it is of 15. Okay. So this is the new structure which has formed after doing the single right rotation. So from this entire unbalanced structure, we did a right rotation and this is what we are getting now. And now if we calculate the balance factor, we are going to get a proper balance structure, because for 66 now the balance factor is going to be 1 minus 0, because the left subtree has a height of 1, correct? For 66, what is the left subtree now? This is the left subtree for 66. The height of this tree is going to be either this edge or this edge. So only one edge is there. So we have 1 for the left subtree minus, what is there to the right subtree? We have only one node, which means the height is 0, correct? So 1 minus 0 is going to be equal to 1 only. For 77, the height on both the sides is going to be minus 1. So minus 1 minus minus 1, that is minus 1 minus minus 1 is going to be equal to minus 1 plus 1, and hence it is going to be 0. Okay. So that's why the balance factor for a node which does not have any children is equal to 0 always. So this is 0. Similarly, for balance factor of 15 is going to be 0 because we have equal number of nodes on each side. That is, for the left subtree we have one node, for the right subtree we have one node, so 0 minus 0. For 11 it's going to be 0, and for 55 is going to be 0 because both of them do not have any children. So now you can see we have all the balance factor values in our acceptable range, and we have successfully converted this imbalanced binary search tree back again to a proper AVL tree. So this is nothing but a AVL tree. Alright. Okay. So let's take this structure forward. Let me erase this one. We have to still insert more values. Okay, so we're done with 11. Let's insert 33 now. So when you insert 33, 33 is smaller than 66. You'll go to the left. 33 is greater than 15, so you'll go to the right. 33 is smaller than 55, so you'll go to the left. So this is where you'll insert as the left child of 55, 33. Correct? Okay. So again there is an imbalance now, because now if you calculate the balance factor for 66, this is going to be the left subtree, and the height over here is the longest path from 15 to 35, which is 2 edges, right? 1 and 2. So 2 minus the height of right subtree, which is 77. There is only one node, so height is going to be 0. So 2 minus 0 is going to be. So this is where the imbalance has happened. Let's calculate balance factor for other nodes. For 33 obviously it's going to be 0. For 77 it's going to be 0. For 11 it's going to be 0. For 55 it's going to be 1. For 15 it's going to be -1. Not wasting any time to show you the individual calculations. By now you should get a hang of it. But yeah, now you can see that the imbalance has happened at the root position 2. So this is kind of like our critical node. And where did the insertion happen? It happened to the left of 66 and then to the right of 66, correct? You can see to reach 33, you have to go from 66 to 15, which is a left, and then you have to go from 15 to 55, which is a right. And then of course you have to take one more left to reach the 33 value. But remember, when you are doing rotations, we are only involving the imbalanced node and the two nodes below it. So at a time we are only gonna involve 3 nodes, and the trail over here followed is a left-right imbalance, right? You have to go from left to right and then you reach your newly inserted node. So this is clearly a left-right imbalance case, and that's how you detect a left-right imbalance, okay? So this is similar to this case. You can see left and then right imbalance. So these are the nodes involved, and in this scenario we have to do a left-right rotation. So basically there are 2 rotations, a left rotation and a right rotation. But the end result that you get after doing a left-right rotation is this. So I have skipped an intermediate step. Okay, so there is a left rotation first and then there is a right rotation. But the ultimate result that we get after doing both the rotations is what we are interested in. Correct? So just observe this structure and the result. What do you see? So in this structure, the bottom value n3 becomes the parent, right? It is taken to the top. When n3 is taken to the top, the left child becomes n2 because n2 is smaller, and the right child becomes n1 because n1 is greater. Correct? Makes sense? 20 has to come in the middle, 10 has to be the left child, and 30 has to be the right child, of course, because the binary search tree principle also has to be maintained. Now apply this same logic on our 3 selected nodes which are in a left-right imbalance. So when you apply a left-right rotation on our 3 nodes, the bottom node 55 which we have selected will become the new root node, correct? It will be transferred to the top. So let's do that. So 55 will come to the top. This is what we are seeing from this left-right rotation case, correct? So 20 was the bottom most value. It came to the top. So once 55 is taken to the top, 15, that is the center node, which is n2 over here, becomes the left child. So 15 will become the left child, and then remaining 66 will become the right child. Okay, so these 3 nodes that we selected for the left-right rotation, after doing the left-right rotation, this is what we are getting as the result. Correct? Okay, so now we did the left-right rotation in one single step. We did not do the left and right 2-step process because ultimately we are interested in the final output. So we can directly apply left-right rotation if we know what is the end result. Correct? Alright, so this is what we got. But what about the remaining values? So now let's observe which are the remaining values which are left. We are left with 11, we are left with 33, and we are left with 77. So let's take the case of 77. 77 is towards the right of 66. What is there to the right of 66? Nothing. So you can simply put 77 there, because as I mentioned, the original positioning, the relative position should be maintained, right? So if in this imbalance structure 77 is towards the right of 66, in the newly rotated form also 77 has to be towards the right of 66. So we'll add 77 over here. Okay, so 77 is done. Which one is left now? 11. So 11 is towards the left of 15. Over here, is there anything towards the left of 15? No. So simply add 11 over here as the left child of 15. Alright, easy enough. 11 is done. Now what is left? Now 33 is left. Now 33 is towards the left of 55. But if you see now, 55 has become the new root, and towards the left of 55 we have 15. But as I mentioned, we have to maintain the relative position. So 33 obviously has to go to the left only because 33 is smaller than 55. So binary search tree principle also has to be maintained. So we'll go to the left, but over here we have 15. So now 33 is greater than 15. So of course it will go to the right. Correct? So 33 will come over here and become the right child of 15. Also, if you observe in the original structure, 33 was towards the right of 15 only. 15 is over here, and to reach 33 you'll have to go to the right side of 15, that is the right subtree of 15, correct? So even that relative position is maintained. And now after the left right rotation, this is what we are getting. So you can see this is a very messy imbalanced structure. I know we made a lot of mess over here, but the result after doing a left right rotation is this structure. Now if you calculate the balance factor for all these nodes, it's gonna be ranging from -1, 0 and 1 only. Okay, so let me just erase the previous structure, this one, and now we will use this as our new structure. In case if you're wondering and if you still want me to calculate the balance factor, so balance factor for 55 is gonna be 0 because both left subtree and right subtree has the height of 1. So 1 minus 1, 0. For 15 it's gonna be 0, for 11 it's gonna be 0, for 33 it's gonna be 0, for 66 it's gonna be left subtree which is nothing, so -1 minus right subtree we have 1 node, so it is 0, so it's gonna be -1, and for 77 it's gonna be 0. So you can see all the values are in acceptable range, which means that now our structure is balanced and it is again a AVL tree. Alright, so 33 done. We're now halfway there and I'm guessing you guys have got a hang of it. Let's speed things up. Let's add 22. So 22 is smaller than 55. We'll go to the left. 22 is greater than 15. We'll go to the right. 22 is smaller than 33. So we'll go to the left. So 22 comes over here. So again, balance factor is calculated after every insertion. So let's calculate the balance factor for 55. Now the left subtree height has become 2. Right, this is the left subtree, height has become 2, minus the right subtree is these two nodes, the height is 1. So 2 minus 1, you're getting 1, still acceptable. For this subtree the height is -1, for this subtree it is 0, for this is 1, this is 0, for this subtree again -1 and 0. I'm speeding a little bit, but I hope you are able to calculate the balance factor quickly. So this is still balanced, so we don't need any rotations now. Let's proceed, let's insert one more value. So 22 done, we are proceeding to 35. So 35 smaller than 55, go to the left. 35 greater than 15, go to the right. 35 greater than 35, go to the right, and this is where you insert 35. Okay, so again, calculating the balance factor, is everything balanced? Seems like it, because the balance factor for the top node is going to be left subtree height, which is still 2, right? We have to see the longest path from 15 to 22 or 15 to 35. We have 1 and 2 and we have 1 and 2 edges. So either path will do. So 2 minus the right subtree, which is 1. So yeah, it's 1. For 15 the left subtree is 0 minus 1. So it's going to be -1. This is also -1. This is 0. This is 0. This is 0. This is 0 and this is 0. Alright. Okay, still balanced, all the values are in acceptable range, which is -1 to 1. Let's move forward, let's insert one more new node. Let's insert 25. So 25 is smaller than 55, go to the left. 25 greater than 15, go to the right. 25 smaller than 33, go to the left. 25 greater than 22, so now we have to go to the right. And of course this is gonna cause an imbalance. Just by looking at it, you can see now things are getting a little messy. So now if you calculate the balance factor, what would be the balance factor? For node 55, which is the top node, that is the root node, this is the left subtree. What is the height of this left subtree? So starting from 15, you have to go on the longest path. So 1, 2 and 3 is the longest path till the leaf node. So now the height has become 3 minus what is the height of right subtree? It is going to be as it is 1. So 3 minus 1 is going to give you 2. So imbalance, correct? Let's calculate it for other nodes also. For 77 it is 0, for 66 it is as it is -1, for 11 it is 0, for 25 it's going to be 0, for 35 it's going to be 0, for 22 it's going to be -1, for 33 it's going to be 1 because left subtree, which is having 2 nodes, so height is 1, minus right subtree, which is 35, so height is 0. So 1 minus 0 is going to give you 1. So for 15, what is the height of left subtree? For 15, we have only one node in the left subtree, so height is going to be 0. Minus, for 15, what is there in the right subtree? So for 15 in the right subtree, the height is going to be the longest part between 33 and 25, which is 1 and 2. Correct? So 0 minus 2 will give us minus 2. Alright, so one more node where the imbalance is happening, and as I mentioned, we have to consider the lower node where the imbalance has happened and start with it as the critical node. So this is the critical node. Where did we insert 25? We went to the right, not left, we went to the right, then we went to the left. So these are the three nodes, and then after that we did this new insertion 25, right? So these are the three nodes which we have to consider, and you can see this is a right-left imbalance. So we went to the right and then we went to the left. So this is a right-left imbalance case, and in this scenario what we have to do? We have to do a RL rotation, which is a right-left rotation. Now remaining values are going to be as it is. So let's first write them as it is. So 55 is going to be at the top as it is. 66 is also going to be there as it is, and 77 is also going to be there as it is. Now whatever structuring change is going to happen in this part, correct? So what is the right-left rotation? So just to showcase you, in right-left rotation, if we have N1, N2 and N3, after doing both the rotations, so we are going to apply both the rotations in one step and not the right rotation first and then left rotation, because we are interested in the end result. So when you apply right-left rotation both simultaneously on this unbalanced tree, the bottom node N3 is now taken to the top. So over here also, the bottom node 22 will come to the top, correct? And once the bottom node N3 comes to the top, N1, which is the top node, becomes the left child, and the center node N2 becomes the right child. So keep this in mind, and even if you can't keep this in mind, just remember that the bottom node has to come to the top, and the other two nodes will be arranged according to their binary search tree principle. That is, whichever is the smaller one will go to the left, and whichever one is the larger one will go to the right. Okay? So this was just to make you remember the structuring. But now let's apply the same concept on our three selected nodes with the RL rotation. So our first top three nodes are going to be as it is, right? Now applying the RL rotation, as I mentioned, the bottom node will come to the top. So 22 will take 15's position. 15 was the left child of 55, so 22 will come over here. Alright? Okay. Now 22 has come to the top. The top node 15 is smaller than 22, so it will be the left child. Correct? So 15 will come over here. And 33 of course is greater than 22, so it will be the right child. So this is how RL rotation works. So we have successfully done the RL rotation on these three nodes. But what about 11? What about 25? What about 35? So 11 was towards the left of 15. Is there anything towards the left of 15? No. So we'll write 11 over here. So 11 is done with the attachment. What about 25? 25 was towards the right of 22. Okay. So right now towards the right of 22 we have 33. So we have to still maintain the relative positioning. So we will go to the right of 22 because 25 of course is greater than 25. But since there is 33 over here, we will compare 25 with 33, and 25 is smaller than 33. So we will go to the left of 33 now, and this is where we will attach 25 as the left child of 33. So 25 is still towards the right of 22, right? In the original structure, 25 is the right child of 22. And in this newly rotated structure, 25 is still towards the right of 22. So that relative structuring and balance is also maintained. And what about 35? So 35 was the right child of 33. Is there anything towards the right of 33? No. So 35 will be attached as it is towards the right of 33. And this, my friends, is now again a balanced binary search tree, and hence it is considered as a AVL tree. So if you quickly calculate the balance factor, you're gonna get 1 over here. This is gonna be 0. This is gonna be 1. This is gonna be 0. This is gonna be 0, 0, 0. Minus 1 and 0. Okay, you can pause the video and calculate the balance factor again yourself for better practice, but this is the result that you're gonna get. And this, my friends, as I mentioned, is a balanced binary search tree, and hence it is a AVL tree. Okay, so let's get rid of this unbalanced structure and we will use this new one as our new structure. Okay, so let's proceed further. I know it's going a little lengthy, but now we have 44 to be inserted. 44 is smaller than 55. Again, go to the left. 44 is greater than 22. Go to the right. 44 is greater than 33. Go to the right. 44 is greater than 35 also. So 44 will be attached as the right child of 35. Okay, now things seem like it's going a little imbalanced, correct? So let's see and let's calculate the balance factor again. So for the root node 55, the balance factor is going to be height of left subtree, which is 1, 2, 3, because the longest path is that. So 3 minus height of right subtree, which is these two nodes and there is only one edge. So 3 minus 1, we are getting 2. Okay. So immediately we are getting an imbalance at the top node. Let me write it over here. What about 22? So for 22, the height of left subtree is 1 minus the height of right subtree is the longest path between 33 and 44, which is 1 and 2 edges. So 1 minus 2 is minus 1. So that is okay. For 66 is going to be minus 1. For 77 it is 0. For 44 it is 0. For 11 it is 0. For 15 it is 1. For 33 it is minus 1. For 25 it is 0. For 35 it's going to be minus 1. Alright. Now seems like the imbalance has happened only at the top node 55. Where did you insert 44? We went to the left first and then we went to the right. Correct? So repeating again, we inserted 45 towards the left of 55 and then we went to the right of 55. So this is a left-right imbalance and the imbalance has started or occurred at 55. This is the critical node, this is the second node and this is the third node. So even though this is where we inserted, the imbalance occurred over here because the balance factor was messed up over here, right? So from that we have to navigate down and select the two nodes on the path where the new node was inserted. So again, this is a left-right imbalance, and in left-right imbalance, what do? We do a left-right rotation. So LR rotation. What do we do in a LR rotation? The bottom node becomes the new root node. So let's write 33. By now you should get a hang of it. So I'm gonna write 33 over here. The middle node is smaller than 33, so it will be the left child, 22. And 55 is greater than 33, so that will be the right child. Okay. So after left-right rotation, that is both the rotations applied simultaneously, this is the end result that we should get on these three nodes. But what about the remaining nodes, right? So 66 and 77 are towards the right of 55. Is there anything towards the right of 55? No. So we can do 66 and 77 as it is. Correct? So no problem with that. What about 15 and 11? 15 and 11 were towards the left of 22. Is there anything towards the left of 22? No. So again, 15 and 11 can go as it is. So maintaining the relative positions and the binary search tree principle. So 66 done, 77 done, 11 and 15 also done. What are left? We are left with 25, 35 and 44. Okay. So where is 25? 25 is towards the left of 33. Now 33 has become the root node. So 25 was towards the left of 33. So of course 25 will be towards the left of 33. But towards the left of 33 we have 22. So we have to compare 25 and 22. So 25 is obviously greater than 22. So it will go to the right. Makes sense. So we'll attach 25 over here. It is still towards the left of 33. So relative position is maintained. Where is 35? 35 is towards the right of 33. So now 33 is the root node. What is there to the right of 33? We have 55. So now 35 and 55 will be compared. 35 is smaller than 55. So it will be attached as the left child of 55. Makes sense? Correct? So 35 is also done. It is still towards the right of 33, relatively speaking. So 25 and 35 done. Only one thing remaining, which is 44. 44 is towards the right of 35. Is there anything towards the right of 35? No. So we can simply attach 44 over here. And now you can see after a major restructuring and major rotation of just these three nodes, all the other nodes have been repositioned in such a way that they are still following the binary search tree principle. And they are also following the relative structure. And also they have now become balanced. And this is a AVL tree. So you can quickly calculate the balance factor. let's not waste time right now. It's still gonna be balanced. Okay, so let me erase this, and now we will use this structure as our new AVL tree. Alright, so we're done with 44. Let's insert 88. 88 will go to the absolute right because 88 is the greatest one. So 33, 55, 66, 77. This is where 88 will go. Are things balanced? Let's calculate. After every insertion, you have to calculate the balance factor. Don't skip this step. So for the root node, what is left subtree? This is the left subtree. The height is 2. Minus what is right subtree? This is right subtree. The height is the longest path from 55 to 88, which is 3. So 2 minus 3, we have minus 1. No problem here. For 22, the height is going to be this minus this. So 1 minus 0, 1. This is going to be 1 again. This is going to be 0. This is going to be 0. This is going to be minus 1. This is going to be 0. This is going to be 0. This is going to be minus 1. For 66, there is going to be a problem. What is that? Because for 66, do we have anything towards the left? No. So it's going to be minus 1. And minus, what do we have towards the right? We have two nodes, 77 and 88. There is one edge between them. So the height is 1. So minus 1 will become minus 2. And for 55, what is going to be the height? For 55, the left subtree is these two nodes. Correct? Let me erase this. There is nothing towards the left of 66. So for 55, towards the left of 55, we have 35 and 44. So height is 1. Minus, towards the right, we have 66, 77, 88. The longest path is these two edges. So 1 minus 2, we are getting minus 1. So there is no problem with 55. So in all these values, the problem lies in minus 2, which is 66. So this is our critical node. The insertion happened at 88. So to reach 88, we have to go to 77 and 88. So these three nodes are in right imbalance. And what do we have to do? We have to do a left rotation, a simple left rotation. So 77 goes to the top, 67 becomes the left child of 77. So let's quickly restructure this and let's do a left rotation. Okay, so as you can see, after doing a left rotation, we took 77 to the top, so it became the right child of 55. Over here you can see, correct? And we took 66 to the bottom, which is the left child of 77, and the right child remained 88 as the right child of 77. Makes sense? Things are balanced now. If you calculate the balance factor, it's gonna be balanced. Not gonna waste time in calculating individual balance factors now. We have one last node to add. So let's add that in this structure. So in this structure, 99 is the greatest value. So it will be added as the right child of 88. And that will again introduce a new problem. That is a new imbalance. So let's see what that imbalance is, where that imbalance is actually. So calculating the balance factor, left child or left subtree, height of left subtree 2 minus height of right subtree. Longest path is 1, 2, 3. So no problem at the top. 2 minus 3 is minus 1. The left subtree of 33 is already balanced. There is no need to mess over here. The insertion happened towards the right. So let's not deal with this part. Let's come over here. For 55, the left subtree is 35, which is 0 minus. The right subtree is this one. And the height is going to be the longest path, which is 2. So 0 minus 2 is going to be minus 2, correct? So this is where the imbalance has happened. Let me write minus 2. What about 35? It's going to be 0. What about 77? It's going to be minus 1. This is 0. This is going to be minus 1. This is 0. Okay. So imbalance has happened at this node. This is the critical node. Where did the insertion happen? At 99. So going 2 steps down towards the right, that is 2 nodes towards the right. And now we found our pattern, which is the right imbalance, correct? And in this case, what do? We do a left rotation. So in left rotation, what do? We take 77 to the top, we take 55 towards the bottom as the left child of 77, and 88 is going to be the right child of 77 as it is, and all the other nodes will adjust accordingly. So let's quickly make that change. Let me just quickly draw everything over here. So 33 is going to be as it is. 77 is going to come at the top with the left rotation as the right child of 33. So we have 77 over here. the left side is going to be as it is, right? So 22, 15, 11 and 25. So there is no need to mess with the left side of 33. That is all sorted. Now once we take 77 to the top, 55 has to come at the bottom as the left child of 77. So I'll write 55 over here. 88 has to be the right child of 77. And now we have to adjust all the other values. Okay, so what are the values left out? We have 35, we have 66, we have 99. 35 was towards the left of 55. Is there anything towards the left of 55? No. So we can directly add 35 over here. Done. 66 was towards the left of 77. So we'll go to the left of 77. We have 55. So 66 will compare with 55 and 66 is greater than 55. So we will go to the right of 55 and this is where we'll put 66. So 66 is still relatively towards the left of 77. Done. Where is 99? 99 was towards the right of 88. Is there anything towards the right of 88? No. So let's apply 99 and insert it as it is. And now this is where we found again our proper binary search tree, which is balanced, and hence it is considered as AVL tree. So this, my friends, is going to be the final answer. And again, if you want, you can calculate the balance factors, but it's going to be in this range itself from -1 to 1. And this is a proper AVL tree using this entire insert sequence. Okay, so I know this took a lot of time and the video went a little lengthy, but I had to show you step by step at every step calculating the balance factor and then doing the different rotations, figuring out where the problem is and detecting and understanding which type of rotation is to be applied and then adjusting the remaining nodes. So once you get a hang of it, you can quickly do it. I know this is not going to be that lengthy for you to solve once you understand it, but for understanding purpose, I had to go a little slow. So I'm going to wrap up this video over here, and maybe if you want many more examples, let me know in the comments. If you've understood this video, if you've understood the entire AVL tree creation using insertion sequence, if you've understood the balancing of an unbalanced or imbalanced binary search tree by doing rotations to the AVL tree, please give this video a like. Definitely share this video with your friends. This is important. You might get this kind of numericals in your exams as well. In fact, also in interviews, you can be given insert sequence and you'll be asked to construct the AVL tree. So this is an important topic. Let me know in the comments if you want some more examples. If you have some examples in mind, put them in the comments. Maybe we can take them in further videos. And I'm gonna wrap up this video over here. Thanks for watching. See you in the next one. Peace.